the outline of this presentation, this webinar is going to be the following. So first we'll talk about Cimerix, the Cimerix cavitation modeling, the advantages, what we bring to the table, which is unique. And then we will have a cavitation demo setup. Dr. Yavachen will set up the piston pump and show the inception of cavitation and talk about some of the advantages of our software in how fast we can predict cavitation and how quickly the simulation can run. And then I'll talk about some of the engineering studies that we have done in the past for some other customers, and that has been published. So the first will be about, in general, pump cavitation. The second case study will be about an axial flow pump. The third case study will be about an propeller. And then I'll kind of let Dr. Yavachen show some of the results from the demo, and then we'll talk about the upcoming webinar and take any questions from you guys. How we do it, I would say it's like a four-pronged attack. So the first part of that is automated meshing. We have our own proprietary binary tree mesh. So this is like a Cartesian grid unstructured, which can complex geometries, and it can capture very fine details with automated meshing and with ease. This high fidelity mesh has quite quick turnaround in helping you prepare the model. So this is a big part of how we are fast. The second part of it is our template driven workflow. So this makes it very user friendly. This is because we have templates for various different types of applications that are catered uniquely to that application. So all you will need to provide is some basic sets of inputs, and then we will be able to kind of set up the process with that without too much hassle for the users. And also it is a very short learning curve for users, even for design engineers, because we have this template which kind of does the hand holding. And this also eliminates dependence on very high-end development. So every time you have a new project, you don't need to research this, and it can reduce the number of manpower hours that is needed for a model setup. So the third part of the equation is moving meshes and dynamics. I think we have shown quite a bit over our past few years that modeling complex motions, be it pump, be it nowadays with bearings, with electric motors, we can do this quite easily and quite robustly. And we can also model the small clearances where we have like these changes from bigger size mesh to smaller size mesh quite accurately. And so that is also a big advantage of why we are the best in the market. So the combination of that is we have a very fast, accurate, and robust approach to solving complex physics like cavitation, dynamics, multiphase, conjugate heat transfer, etc. And we would say that we are multiple times faster. This is something that we have heard from many of our customers. And we have validated several different industrial applications across different verticals. So in terms of our software suite, we have the Cimerix CFD, which has been there for a while now. We have the Cimerix FEA, and then we have the Cimerix OPT. So the CFD has multiple physics in there. So we have the multiphase with the volume of fluid approach and the cavitation. We have the heat transfer, the turbulence. And in the last few years, we have focused a lot on the CAD integration with some of the CAD packages like Creo, SolidWorks, NX, Fusion, Rhino. And we also have integrations with other tools like GT, SimScale, Cases, CF Turbo, Orca 3D. So we have a wide variety of CFD development, and now we are marching into the area of FEA. So the FEA code has been developed the last few years, and it'll be released soon. So this is to kind of help solve some of the coupled CFD problems with FEA. So that is our motivation, is to have a tool which can do both of it together. And as we have seen in the last year after the release of the optimization solver, so we can see that it can bring a lot of design improvements while we couple the CFD along with the optimizer inside our own kernel, which is our native optimizer. Sorry. So the next part of this is the Simerics cavitation modeling. So let's talk about the cavitation physics briefly. So cavitation is essentially the formation of vapor phase of a liquid when the local pressure goes below the saturation pressure. This is at a particular temperature. So what happens is the vapor bubble will start to kind of grow, and it can travel in these low pressure regions. These bubbles, when the pressure gets higher, will start to collapse, and this can generate a shock wave in terms of the force, essentially. So this can damage the surface of material. It can affect the performance of the device at hand. So to predict cavitation mechanism, during design phase could be very useful in ensuring the life and reliability of the component. So here we are showing a picture of how a bubble gets formed at the low pressure zone. As the pressure increases, you'll see a breakup of the bubble and then collapse. And the collapse of the bubble can be how it collapses can impact how that jet travels and how it impacts your surface. So what is the challenges to modeling cavitation? I would say, cavitation modeling, formation and transport of these vapor bubbles has been in literature for a very long time. It's not something that is recent. I would say practical and robust cavitation modeling is available only in few codes due to some numerical challenges. I think the numerical challenges are mainly the large density gradients, differences between the liquid and the air or the vapor phase. These density ratio differences can be, the ratios between the high density and the low density can be in the order of 10,000. So what happens is any small changes in the non-cavitated regimes can get amplified 10,000 times in the cavitated regimes. So this numerical instability can be hard to address if not handled properly. So in our cavitation model, I think we solve the standard Navier-Stokes equation. So with variable densities with multiple phases, and we have a standard K epsilon formulation for the turbulence. So density is essentially based on two components, right? Based on the vapor and the liquid, based on their respective fractions. And so what we do is for the vapor mass fraction, we will use the conservation equation below. And you notice that it's the standard conservation equation, but we have the evaporation and the condensation terms, which will be the source and the sink terms into this conservation equation. So we are showing here the evaporation and condensation rates, how they are formulated. So the other part of the equation here is the non-condensable gases. So if you talk about any real engineering applications, it's not just also a combination of other non-condensable gases, be it dissolved or free in the liquid, that can be important and that needs to be modeled. So what we have done is essentially we have reformulated the above equation and we have included the non-condensable gases. So what happens in low pressure zones, you will have some localized expansion of the bubbles. So this will be, then first an aeration. So some, let's say free or dissolved gases will get generated, and then you will have the vapor formation as the pressure keeps dropping below the saturation pressure. And so the density, velocities, and pressure distributions will change based on the localized effects and how much gas and vapor gets generated in those regions. So essentially a reformulation of the density for the formulation that I showed before is now we have the vapor as well as the non-condensable gases G included in our equations. So the total, say, liquid fraction will be nothing but the one minus the vapor and the non-condensable gases. So that is kind of a rough idea of how our cavitation model works. I would say the trick of how the implementation is done is something that is proprietary in nature, and that is our key strength. How we integrate the Navier-Stokes equation with our mass fraction equations, and how we do that efficiently is why our software runs robustly without any issues when we talk about cavitation. So in terms of advantages, I'll kind of quickly gloss through some of them. So the first thing is it's very easy to set up models. It's quite accurate. We will show some of the cases that shows this, and it is robust even when you have moving deforming meshes. And we have quite fast simulation runtimes, and we have wide array of models that can capture complex physics. So in terms of the ease, I think the model is quite self-explanatory. So I'm talking about, say, this constant gas mass fraction model. So all you'll need to do is add that cavitation model and set some basic parameters like the amount of gas in your liquid, the free air in your liquid, at say equilibrium pressure or reference pressure, and then the saturation pressure and the temperature, and that's all you will need. And you just need to solve further, and we will take care of the rest of the physics that's happening inside. Similarly, even for a complex model like a full gas model, all you'll need to do is add some extra terms. For example, here we require the gas dissolve gas release time, dissolve gas dissolve time. Once you add those and set the rest of them, you will be taken care of in terms of how the air forms, the free air or the dissolved air, get formed and moved around the system. And the other thing is the inlet or outlet. You will essentially provide how much is the air coming in or going out, and that's an extra input that you will need to provide. And that's all you need to do to set up these cavitation models. In terms of accuracy, this is one case study that I wanted to quickly show is the inception of the bubble and the collapse of this bubble, for example, in this groove region near this piston pump, and what they have seen in the physical testing of the wear spots, and we were able to capture that quite accurately. We also know multiple applications where we have run this moving mesh capabilities. So you can see essentially how we can capture these bubbles even in a very small gap. These are the shoes inside this piston pump, and we can, even in the small clearances, we can capture these cavitation bubbles happening. So in terms of simulation runtimes, you can see that we are modeling here a 16-cylinder Caterpillar engine, and we have multiple bearings which are of very thin clearances. We have the say the journal bearings, the connecting rod bearings, the piston pin bearings, and the cross drills. And you're looking at the cavitation bubbles and the aeration that is happening inside the system. So the magenta essentially is vapor or gas that gets formed, and then the blue is the liquid. So you can see sometimes when your the crankshaft is rotating around, you'll see some entrainment of air. So you can see this magenta color get formed on this bearings, and then when the oil gets fed through the cross drill, that gets washed out. So for this system to run this simulation for us, it takes relatively short amount of runtime. So that shows the complex nature of our modeling capabilities while doing it in a very fast turnaround time. Also, we have a wide array of cavitation models. I think we briefly talked about a couple of them before. So here I kind of list all of them and explain briefly what each one does. So the constant gas mass fraction model essentially models the free air and the vapor. So essentially what it means is the non-condensable gas is constant and considered to be out of solution, essentially. So you will have, let's say, low pressure formation, then you will have some free air gets formed, expand, and then at high pressure it kind of collapses and becomes liquid. For a variable gas mass fraction model, it's similar to constant gas, but only thing is now you can kind of control the inlets and outlets with different mass fractions of air coming in and out of the system. Equilibrium dissolved gas model, now we have an extra variable, which is the dissolved air. So we have the free dissolved air and the vapor along with the liquid model. And essentially what we assume is that at equilibrium, there is a certain amount of free and certain amount of dissolved air. And as the pressure changes, the equilibrium pressure changes, that proportion will keep changing accordingly. For the dissolved gas model, we have again the three phases, the free, dissolved air, vapor, along with the liquid. And here we have some absorption, desorption rates at equilibrium value. So you can kind of control how fast or how slow the dissolved and the free air interact with, go out in and out of solution, basically. And the full gas model is basically the full combination of everything. You'll essentially be doing the dissolved gas model, but combine it with the variable gas mass fraction. So essentially, it's kind of a more complete model. So the next part of this talk, I'll kind of briefly introduce the problem with this piston pump, and then Dr. Yavichin will show you how to set up this model. So here we are looking at this piston pump, and you're looking at a cavitation erosion damage on the valve plate, and you can see our simulation can capture that. For this demo, we are using the swash plate piston pump. So the swash plate angle is about 17.48 degrees. We have the piston cylinders, we have the valve plate domains, and then the outlet is around 100 bar, and then the inlet is at atmospheric pressure. On the right side, we are showing an animation of the pressure profile as a function of time. So you have the inlet port, low pressure is getting fed into these pockets. You can see the squeezing of this mesh, squeezing of this fluid as it gets contact with this outlet port, and you can see this pressure wave travel outwards and towards the outlet. So this is essentially like a pressure animation of our simulation. So I'll stop here.
Yeah, thanks, John, for the introduction, and thanks everyone for being here. So I'm gonna do a live demo of how we built this swash plate piston pump in Simerix in a very short time period, and also how we can get the solution fast and also visualize the cavitation through this simulation. So this in this geometry, we essentially have this inlet port, and we also have this discharge port, and we have this piston fluid domain, and we also have this kind of this valve plate to connect the piston and the inlet outlet port. So first, we will start with the mesh, and to build the mesh, I simply select this inlet and outlet port together, and then I come to this mesh tab, and in Simerix, as John mentioned, we have the boundary tree measure. So what I need to do is simply kind of put all those CAD surface and feed it here, and now I can kind of measure it. Let's say this is this dialog allows me to change the mesh size. For instance, I'll make the maximum cell size global as kind of 0.01. This is a relative cell size, and I'm gonna give it a kind of a cell size refinement on the boundary, make it 0.005. Then I'm able to generate the mesh. So you can see after you click it, it's kind of create two volumes, inlet and outlet. And I can go to the result and turn on the grid. It shows you the how the mesh looks like. You can see we have a very high quality mesh. And then we have this next, I have this kind of the valve plate, which is used to connect kind of the pores and the piston. For this valve plate, we'll do similar thing. And I'll put this valve plate together. Since this valve plate, there's 5 volumes, and they are just a single one. 5 volume, but I want to group them together. So to group them together is also very easy to do. I simply kind of select this valve plate, and then here there's the option called multiple volume. I'll say, okay, single volume. Essentially, I'm gonna group those 5 individual valve plate into a single one. So this valve plate, it has critical features like this kind of pressure relief groove. So I want to give it a little bit more refinement. Let's say I make the maximum 0.005, and cell size on the surface, I'm gonna refine it by one more level. So you click this kind of create mesh, you see now it creates this the valve plate mesh form as well. So lastly, we have the piston. So for the piston, as Terence mentioned, we have kind of developed special template to allow the user to quickly build up the model. Since we are modeling this swash plate piston, I'll go to this rotor template and measure, and then I'll select for the rotor tab, I'll select this swash plate piston. So for this swash plate piston, once you select it, it asks you for a couple of input. Let's say, what is the piston wall? And piston wall, here we have this piston wall, essentially is this piston end. and also this piston wall. Essentially, it is the boundary that moves together with this piston. It will do the translation and also the rotation. Then you have the cylinder wall. Cylinder wall is the boundary that combines and shrink. So if you look at this geometry, this is our cylinder wall. And we also have this piston cap. Piston cap is the boundary that just does the rotation along with this piston. There's no translation along the axial direction. So we have this piston cap. Lastly, we have this piston MGI. The piston MGI is used to connect the piston with the valve plate. So you can see the user just need to fit those different CAD surface into different category, and pretty much that's it. So then we just need to specify the number of pistons. We have 9, and rotation axis is in the z-axis. So we have 0.01. So for the switch plate center, it's just the default center at this origin 0.000. And for the cell size, let's say I'll give the maximum size as 0.1, and size on the surface, I'm gonna give it one more level of refinement. So pretty much that's it. And then just kind of click this build switch plate piston, and you can see automatically it built all those piston volumes to me. So the switch plate piston pump itself is a complicated system, but you can see in 5 minutes, the model pretty much is done. So once we have the, let me save it. Once we have different volumes, and next step is to build up the connectivity between the volumes. Let's say my inlet, the flow comes from the inlet, it's gonna go to this valve plate and eventually sucks into this piston and then push it to the discharge port. So to connect it, I just need to select their neighboring kind of boundaries. For instance, for this inlet and outlet, I have this inlet MGI, I have this outlet boundary, and it's gonna connect it with my valve plate. So valve plate, I'll select the valve plate MGI to the port. And then you select these 3 boundaries and create the MGI. MGI allows kind of the fluid to transport between different volumes, especially when you have a moving sliding mesh versus the stationary mesh, or you have 2 volumes that the mesh is not conformal. So we built up connectivity between the valve plate and the ports. Next is we'll build up the connectivity between the valve plate and the piston. So to do it, simply select this valve plate to the piston, and we also kind of select for the piston, we have one boundary is the piston MGI. So you just need to kind of select those 2 boundaries and then create an MGI. So pretty much that's it. So we built up the connectivity among different connecting volumes. And after that, so you see automatically we have this switch plate piston, and we are gonna add some physics. For this, we want to study the cavitation. So you see cavitation, to add the cavitation is very easy. You just need to go to this module and go to this flow, and then we can add the cavitation. By default, we'll use the the constant gas mass fraction, the first cavitation model transmission, and then we can set up the switch plate angle. So for the switch plate, and we have the switch plate center is 0, 0. For the switch plate normal, we have so this is minus 0.315, 0 and 1. So this is the switch plate angle. So once you set up this switch plate angle, when you run this model, automatically you'll see the switch plate start to tilt. So basically you'll see the volume of the piston, they will expand and shrink to create this charging and discharge of the fluid. So rotation speed, let's say I'm gonna give it 1800 RPM. And rotation direction, I'm going to use the default clockwise rotation. So we configure the rotation and the switch plate's angle of this pump. Next step is to set up the boundary conditions. We have the inlet. We simply put it as inlet and 1 atmosphere pressure. And then we have this outlet. Outlet, I'm going to also give it a pressure outlet boundary condition with 100 bar high pressure outlet. So, and if you want to change the material properties, you can select all the volume and change the dynamic viscosity, density, and some other parameters. But I'm going to just use the default to kind of for this demo case. So yes, that's it. So this model is ready to go. And you can clearly see that within 10 minutes, we pretty much finished the build up of this complicated model, and we are ready to run this simulation. So I'm going to let it run. So you'll see I'm running it. Let's say we run it for one complete rotation, and for each piston kind of piston movement, we have 30 time step. That means we're going to have 1800. We're going to have a 270 time step in total. So let's run this model. And I'm running this model on my kind of laptop. You'll see how fast it runs. So let's start. And once you start, kind of you can see the switch plate start to kind of change the position. And essentially, we have this kind of, this is our inlet port. As this piston kind of expands, it creates low pressure and sucks in the fluid from this inlet port, and then the piston start to shrink and compress, push this liquid out to this to the discharge port. So we can visualize how the cavitation bubbles looks like. And first, let's look at the pressure distribution. So this is how the pressure looks like. And you can see we have a high pressure at this kind of discharge port. And as this piston moves, what you will notice is, first, this piston compressing is not the pressure is not compressed enough yet. But at the same time, these pistons start to touching this high pressure part. So what's going to happen when you have a high pressure part and a low pressure piston? So you're going to create a very strong jet, and that jet will shoot into this this piston, and that will generate the cavitation bubbles. It's actually similar for this near this inlet port. Near this inlet port, when you have this high pressure piston, and this high pressure piston volume start to connect with this low pressure inlet port, and then suddenly you have a release of the pressure. It creates a strong jet. So this is the pressure distribution, and we can create another video to visualize the cavitation bubbles so that we can kind of put those side by side. And we have this pressure, and then let's say I can create isosurface of this total gas volume fraction. And to create isosurface, I just click this button and it creates this isosurface. And I can plot the total volume fraction of the gas. Essentially, if you let's say if you have 50% gas, that means you're gonna have a large bubble. So let's say we plot this total gas volume fraction, and you will see kind of how this cavitation right now cavitation happens at near this inlet port. When you have this high pressure piston connects with this low pressure inlet port. So as it moves, you'll see we're gonna see another cavitation happens near this pressure relief groove when this high pressure discharge port connects with this relatively lower pressure piston because it's not compressed enough yet. You can see there's a large bubble kind of being generated, and if you plot the vector, you will see the vector actually it shoots into this this piston. You can see how fast it runs. Right now, it already runs kind of a 2-pocket rotation, and pretty much the system already stabilized. And we can also kind of, let's say, we can plot this pressure distribution along with this cavitation together. So here, let's say I'll select the plot this pressure and make some kind of transparent change. And then we can plot these cavitation bubbles and also visualize this cavitation bubble together with the pressure. So let me turn on the vector, and you can see where the cavitation happens. Yeah, so kind of cavitation is a natural process. Sometimes you cannot prevent, but there's always some ways to identify why the cavitation happens and where does it happen, so that we can come up with a plan to improve the product design to reduce the damage caused by the cavitation. And from this kind of a simulation, you can see that within kind of 15 minutes, we're able to build this complicated model and also visualize the cavitation location. And kind of later down it involves some optimization of this kind of groove design so that we can minimize the impact of cavitation. Okay, yeah, that's it from my side, and I'll hand it over to Chirons.
Thank you, Yahweh. Let me share my screen back. Hope you all can see my screen. So I think the steps that Yahweh detailed, so it's, I would say, first we try to get some fluid extracted out of the solid model. You mesh it. Our meshing is, as we detailed, it's an automated mesher, and in many cases we have a template which kind of does the meshing with a nice structured mesh. And then you create the interfaces. We call them mismatch grid interfaces. Our mismatch grid interface actually is an implicit algorithm that kind of is conservative between the two domains or multiple domains that you attach together. And it can handle moving mesh on one side, stationary on the other side. It can handle also high aspect ratio cells on one side and normal cells on the other side. So it is quite powerful algorithm that we have written from scratch. And we have then adding the physics modules that you want to solve. In this case, cavitation is the main thing that we are looking at. And then you set up some boundary conditions and the properties and start running the simulations. So let's talk about some of the case studies. So I would say first, in the case study of pump cavitation, I just put a broad brush topic here and show you some of the examples to give you a panoramic view of, in general, what is our capability in terms of cavitation. So here we are showing a vein pump cavitation. So what we are plotting here in magenta is essentially pockets of vapor or air getting formed. The volume fraction of that is 1. So that will be the magenta color. And what you will notice as you keep increasing the speed of the pump is at some point the cavitation effects get quite significant, and then you will start to kind of the flow rate of your system starts to deviate from the linearity, and you will kind of start to create this plateau. And this is essentially experimental data and Cimex data, which is kind of on top of the experimental data. And the same case for a gyrotor pump. So this is the idealized flow rate coming out of the pump at different speeds. And then you have some difference in the experiment due to leakages, which we can model as well, very tiny clearances. And you can see we can, capture that leakage effect inside the pump. And at the inception of cavitation, you'll start to kind of move away from the linearity. And then that's when it starts to plateau, and we can capture that in this case as well. So the other thing that cavitation does, it's kind of offsets the pressure rise. So it delays the pressure rise. And that, again, is a function of RPM. So at higher and higher speeds, because the cavitation bubble gets larger and larger, you'll see a more offset of the pressure rise. So this is what this is numerical results at different speeds. And we are showing how, the cavitation causes the delay in the pressure rise as a function of the angle, basically. So this has been published in Aachen conference in Germany, the International Fluid Power Conference, essentially, in Aachen. The second engineering case study that I want to show is on this axial flow pump. So this is a paper I wrote in the ASME. So it's in the public domain if it's of interest, can be shared with any of you. So this is essentially like a loop test that they've done with axial flow pump in the middle of it. And they have a flow visualization window to kind of look at how the cavitation bubble gets formed in these blades, essentially, of this pump. And they run this at different speeds. So first, let's talk about the model. At that time when they had done this simulation, we had modeled with about 1.1 million cells. So we are dividing this geometry into 4 different domains. So the inlet domain, attaching to this impeller domain, and then that is attached to the diffuser domain, and then going to the outlet domain. And of course, we use this MGI algorithm, which we briefly talked about, to connect these domains together so the flow can go from the inlet all the way to the outlet. And also we are focusing here on the small gap, which we can model as well at the impeller tip, and we fully resolve that gap. For the simulation conditions, I kind of list the conditions that were run here. So the speed is listed here because this is a scale down model. So it's run as 325 RPM, and then the flow rate ratios that were used for the simulation is also listed here. The properties of the fluid is pretty much like coolant, and then you have the density, viscosity, and also the vapor pressures, as well as the air content that we are using in the model. So this is how the GUI looks, which Yahweh actually talked about a little bit in detail. So here we are seeing essentially the induction of the cavitation bubble by this cross flow through this small gap. And also we have an animation here visualizing the cavitation bubble that gets formed on this blade, basically. On the bottom right side, we have this pressure and velocity distribution, kind of showing how this flow comes in and how the velocity field looks like on this cross-sectional view. So here I'll show you the animation of this. So this is how the visualization window that was in the test showed this bubble. It's kind of forming on this suction side of this blade. And we can see this bubble clearly captured in our cavitation modeling inside our numerical software. So this is at, I think, % or 80% flow. I'll show that in the next slide. So let this run through. So yeah, so this is essentially at 80%. That was the video you saw. But, the different flow speeds, they had videos, and we also kind of compared our numerical results at different speeds using the same criteria for the cavitation bubble. So you can see here a comparison at 60%, and this is at 80%, and this is at 90%. As you keep increasing, you'll see the bubbles start to get smaller and smaller. And this is at 100%. You can see the bubble is almost disappearing, basically. At 120%, you can see a very thin bubble on this side, basically. So this is essentially like one of the validation studies that we show at different flow inlet conditions. We are able to capture the inception and the size and the nature of the bubble quite accurately on this actual. So the next one is this propeller study. I have like bunched a few propeller studies into here, but I'll talk a little bit more detail about this E779A propeller. So this is essentially this Italian ship model basin in Xi'an, in short. They did a series of experiments for this E779A propeller. So this is to kind of look at the performance and the cavitation characteristics. I think this model has been there used by researchers to look at benchmarking the CFD simulations and looking at cavitation on this propeller. So yeah, the source data for this propeller geometry and also the test data were obtained from Xi'an. And we had like these papers that we used to kind of get some of these data from. So for the facility, it looks something like this. So you have like, again, like a camera that is kind of recording how this, bubble is forming, or the cavitation patterns are forming on this propeller, which is kind of rotating inside this water tunnel facility. And then you kind of look at some of the images, and then also they're measuring a few characteristics so that we can compare quantitatively some of the numbers. So let's look at some of the parameters that was used. So we were running, I think, 3 cases: advanced coefficient of 0.71, 0.78, 0.83. Advanced coefficient essentially is the ratio of the inlet flow velocity divided by the rotational speed. And then also looked at, for this cases, we have 3 cavitation numbers: 1.76, 1.78, 2.06. Cavitation number essentially is characterizing the outlet pressure to the saturation pressure divided by, again, the speed, I believe. So the water is used as the medium with the density viscosity shown here with the same vapor pressure as well as the air content that we used listed here here as we used in the model. For this model, so this was done, I think, a few years back. So I would say the mesh is like on a smaller side. It's about 850,000 cells. And of course, the propeller location, we kind of do a refinement zone. So we can actually choose regions where we can localize the refinement zone using our user-defined functions, basically. So the propeller and the surrounding zone, we created a finer mesh compared to the outside mesh, which is coarser. So here, first I show the performance data. So for different advanced coefficient, and we are looking at the KT and the KQ. So essentially, we are looking at the performance curve for this propeller, and you can see the data. We can actually quite closely match the simulation. The simulation data quite closely matches with the test data, essentially. So this is for this propeller. So let's look at the cavitation, which is essentially of interest for us. So you can see the cavitation bubble formed at the tip here on the suction side, essentially. So now we are looking at different conditions and how the bubble looks for comparing to the test data. So I think I would say, as we know, the quantitative numbers are good. So now we are looking at essentially qualitatively the size and the shape of the bubble that gets formed. And for this J 0.71 and sigma 1.76, we can see that the bubble looks quite similar to what they captured in the test video. As you keep increasing this number, the J number, as well as the sigma, you can see the bubble starts to reduce in size. And that's true in the test as well as the simulation, and the size and the nature of it looks quite identical. And then finally, you can see at the highest number of J and sigma, we can capture the smallest here, and you can see that the test shows something similar as well. I also put in here, so we have like a nice bubble tracing animation of how this bubble or this flow happens. And I here I have one more validation for the screw propeller 4119, and you can see a comparison between the coefficients, the KT and KQ, for basically the experiment compared to the Simerics. Again, we have matching here between I would say the maximum difference is around like 4% or something compared to the test data. One more propeller that we run recently, which is this VP1304 propeller. Again, I have this characteristic curves here showing quite a good agreement for this KT, KQ, and also the efficiencies, basically. So we again see that the numbers are within 2 to 4% of the experimental data. For this VP1304 propeller, we also kind of have some plots in the paper of how the cavitation bubble looks like. And I think we get very good correspondence to what we find in our results to what they have seen in their data, or reported in the paper as function of the test. So what we would see here is this tip vortex. I think the test was seeing this tip vortex, and we can capture this quite well. And also we find we can capture this root vortex, which is what is seen here as well. And also we see some hub vortex, which is, I think you can see somewhere like picture there. But so yeah, so we kind of see all the three different types of vortex that gets captured in our simulation basically. So it kind of depicts the the power of our cavitation capability. So I think these were the three case studies that I wanted to discuss. Now I think I'll stop here, and
we run kind of one complete rotation of the of this pump, and let's say we can quickly check the inlet and outlet flow rate. If you select this inlet and outlet, and we can plot the volume flow rate. And this shows you the volume flow rate. There's a fluctuation at the outlet, and we can also, let's say, do this if we took a average of the, let's say, 30, which is the kind of each pocket rotation average, you can see it actually stabilizes very fast. And now let's say I can use this to quickly create animation. And I select this kind of cavitation bubble and also my inlet and outlet, and then go to this result and save animation. You can see I have those results being saved. And so it runs very fast. You can see I start from kind of 10:58 in the morning, and after kind of it finished at 11:12. So essentially just 14 minutes of simulation. And I'm using kind of my laptop, which is kind of with i7 kind of 13th generation course. And let's say we select those results, and we can quickly create an animation. So cavitation. So essentially, it's gonna load the result one by one, and then generate this animation. You can also see we have this selecting mesh, and those cavitation bubbles or the jet kind of it's being generated each time when the piston volume touches this connects with inlet and outlet port. So the total mesh for this model right now we are looking at about 160,000 cells, 160,000. So it's not a very big model, and we are able to run it very fast. Even let's say you add more physics, for instance, add the more leakage and the shoe size, the model probably will go to about 1 million, and we can still run it and get the results in very kind of fast time. So we have this kind of animation. Let me quickly play it, and it essentially shows you the pressure kind of distribution along with this cavitation. You can see we have the cavitation happens near this pressure relief groove. But then another thing is this cavitation, if the bubbles shoot into the piston, the damage will be maybe not so significant, but if the cavitation happens near the groove, and you probably will end up with damage this valve plate, as shown in the picture kind of what Terence showed earlier. Okay, yeah, Terence, that is all from my side.
thank you, Yahweh. And that kind of shows you like how we model the cavitation and how we can visualize the results. So the next webinar will be in 2 months' time. So the first week of April, we'll talk about gearbox modeling, something that again we have a unique template that kind of does the heavy lifting. So if that's of interest, please feel free to join us. We'll send you a reminder as well. Yeah, now we get to some questions and answers. I see some questions already in the chat window. Let me. So the first question is, Yeah, I wonder if from Max, I wonder if this will be recorded. It is getting recorded, so we'll upload this to YouTube once it's processed. We will send you guys a message. From Todd Moser, I'd be interested in how you define the moving mesh for the piston pins and the connecting rods. So we have expression based editor, which is our native kind of, let's say, scripting that we kind of write expressions to do some of the moving meshing and squeezing meshing that we do that I showed you. So, but for these kind of piston pin motion, piston rod motion, and also like this crankcase, all those we have already kind of developed something that can be utilized. We don't need to write it from scratch. It's already there. We just need to modify some of the input terms. So if you're interested, please contact me and I'll get you the correct material. From Sheetal Jain, in constant gas mass fraction model, the gas or air is always free, or it dissolves into liquid as pressure increases. It's always free air, and it will kind of reduce and go into liquid. It will not become dissolved, but it just becomes liquid as the pressure increases. So there is only free air in the constant gas mass fraction model. From Hannah Boland, in the constant gas model, there is no transport equation solved for the gas or air going in and out of solution. The gas mass fraction is fixed and always free, but the volume fraction varies. It basically simulates small bubbles that are always present in the fluid and never dissolves. Yes, Hannah is essentially helping us answer Sheetal's question, so that's fantastic. From Raj, the difference between the SWOT cavitation model and the Cimerix cavitation model is that the addition of non-dissolved gas volume fraction. Yeah, I think that is one. I think there is some also implementation differences. There's some finer details that probably requires a longer form conversation. But I think in general, I think it's similar, those two models, but we do have like these non-dissolved gases. So that is an extra advantage that we have. From Daniel, you have shown comparisons between cavitation and erosion damages at the valve plate with your simulations. Which quantity do you use to localize the erosion in your simulation? How do you predict the erosion intensity? Actually, there are two points to this answer. One is essentially in our cavitation model outputs, we have some terms which can visualize essentially the power. So that power is based on essentially the velocity, the velocity differential and the pressure differential, velocity change and the pressure difference. So based on that, there's a power term that we have. So the power can kind of give you some quantitative idea of how much potential there is of damage. So we have some threshold above which damage is likely. On the second part of the answer is essentially we also have an erosion model, which is kind of uses some of these terms to kind of model the removal of, let's say, solid material, like essentially the changing of the fluid space. So that model is something new. We kind of still developing things in that, but I think so both these together can actually help us, let's say, predict the erosion intensity. So if there is of some interest, we can definitely kind of send you some material. So the next question from Raj is: does Cimerix cavitation model consider the surface tension in the Rayleigh-Placid equation? It is often neglected in other models. I can actually quickly show you. What I understand is there is a term in our evaporative RB term. So this RB term actually takes into account the balance between this aerodynamic and the surface tension forces. So it's kind of indirectly modeled, the surface tension term. It's not a direct, because in this equation, surface tension term is ignored. So, but it is accounted in a different way. So it is taken into account. Is the answer to that question? So Hannah Boland, Cimerix utilizes the single cavitation model. It has some other numerical references from Swartz Gerber model in the way the bubble dynamics are handled. Single cavitation model treats the fluid as homogeneous, while Swart has it applied as either a homogeneous model or Eulerian phase in the past. Yes, I think Hannah is perfectly answering all the questions. So, so the next question is from Gabor. Which cavitation model is the most accurate for centrifugal pumps? I think we found that the constant gas mass fraction model will do a good job for most of the applications. But in some cases where you need, for example, the bearings where you need the inlet outlet air to be specified, so you have to use the variable gas mass fraction model. And also in some cases where I think I would say the dynamics are more complex, where it is important to understand like some time constants to your, dissolution of gas into liquid or getting into free or dissolved gas. So in those cases, we know that we have to use the more complex models. But I think in general, just for centrifugal pumps, I would say the constant gas mass fraction model it does a very good job. So the next question from Zihao is, can the cavitation model be coupled with VOF or they have to be used separately? So right now in our current implementation, these two are completely separate models. Our hope is in the future, in the VOF, we will have cavitation model included as well. But currently it's a separate implementation and you have to use it separately. The next question from Gabor Lechner is, how is impeller blade surface roughness taken into account in cavitation? Yeah, right now we have a roughness on the surface. You can kind of provide a roughness height, but this is not taken into account explicitly. So it's just in our flow solver, it'll be a term basically. So in the cavitation model, it'll be affected based on how we solve the flow field. So that's what I would say for this question. Next question from Ben is, are there situations where we should use a smaller value for the total gas volume fraction isosurface, such as visualizing incipient cavitation in a centrifugal pump, or is a fraction of 0.5 the best value to use? Yeah, I think this is kind of based, I think we have like, I would say 4 or 5 different variables that kind of helps us look at cavitation more in detail. So 0.5 is a number that we used, which means that it's very clear that there is cavitation happening. But if you use a lower number, that could mean that it's just early phase, early start of the cavitation. So I think this is something that we cannot say for certainty. It's something based on looking at probably 2 or 3 different parameters together. We can make this judgment basically, which number is the best value to use. From Preetham, what is the convergence criteria used for the cavitation simulation in case of centrifugal pumps, and what is the best practice? So I think it depends on if you're running it with a steady state formulation or transient. For steady state, we typically converge it to 3 orders. For transient, we converge it to 1 order because you're doing it every time step. You're converging it to 1 order. Also, please note that our convergence is relative. It's not absolute. So that means we are comparing our convergence to initial delta E that we created when we started the first iteration or first iteration of the first time step. So when we talk about 1 order, that means that that delta E term compared to currently how it is compared to the first time, we are comparing that ratio. So if that drops to 1 order, that means that ratio has gone 10 times lower. So that's essentially how our convergence criteria works. So yeah, that is based on that. I'm saying you do 3 orders for the steady state for the centrifugal pump, or 1 order for the transient simulation. So the next question from Irina is, do you have an example of the coolant centrifugal pump? Yes, we actually have a couple of papers on this coolant centrifugal pump. If this is of interest, I think I'll contact you, Irina, and I'll share with you some of the materials regarding that. So the next question is, Ziha, what is the cavitation damage model? Is that from an existing literature? I think the cavitation model is based on, it is based on essentially some literature, which again I can share with you. But we also have like some improvements to that. Also, we have kind of formulated our own way of looking at some of the things. So it is a combination of existing literature plus some of the work that we have done in this area. So that is again something we can share with you if it's of interest. From Sachin Kulkarni, for a coupled model, can we couple the software like LS Dyna, which can give some complex motion to the mechanical boundaries? Yes, this can be done. It's all we need is basically how your surface is going to deform. we can take that, let's say, spatial map, and then we can morph our geometry using our expressions to kind of couple back and forth. So I think this is something that we have done in the past. I think there is a paper out there, and we are studying with the Ford noise vehicle harmonics team. We were coupling it with the software name is kind of eluding me now, but essentially it's a structure tool. It'll modify the geometry of the blades a bit, not blades, the pump, the pump, the gears a bit, and then we kind of go back and forth. And I'll note this point down, and I'll give you that paper if you're interested. But this can be done. We have done this in the past. The next question from William: how does NCG change in a centrifugal pump? Only volume fraction changes with the pressure. Yeah, so the NCG is basically dependent on the pressure. So yes, the volume fraction changes, and that's how the NCG changes basically. So I'll go through this more quickly since we are already over time. So next question is from Sasha Henok. Thank you very much for the interesting presentation. I'm looking forward for the next upcoming sessions. Yeah, we're glad that you like it. We'll be happy that you join the next one as well. Next from Luke. Do you have any best practices or difference in cell size between meshes and the MGIs? I think these best practices sometimes are baked into our template. So, and also I would say, if you are in a bind, we can go all the way up to 8:1 aspect ratio difference between the meshes on either side. We can still handle that. But I would say, in any case, any CFD software, I would say the best practice is to keep it 1:1. But that's essentially our. We can do it much more aggressive than that if you need to, basically. Yeah, so that brings us to the end of the webinar. Thank you for all the questions. Thank you for your time, and we are extremely excited to share more of